Hi, in this lecture we are going to talk about the counting sort. So, let's get started. Basically, what is this counting sort? It operates by counting the number of objects that have each distinct key value. It is an integer sorting algorithm. We assume the values to be integers, so we are not able to sort floats, doubles, characters or strings with the help of counting sort. For example, we can sort any kind of values with the help of merge sort, quick sort or bubble sort. Here, with counting sort, we are able to sort integers only. Counting sort uses arithmetic on those counts to determine the positions of each key value in the output sequence. It is only suitable for direct use in situations where the variation in keys is not significantly greater than the number of items. It can be used as a subroutine in radix sort. And because counting sort uses key values as indices into an array, it is not a comparison-based sorting algorithm, so linear arithmetic running time can be reduced to even linear running time. So the running time is going to be ordo n plus k, where n is the number of items we want to sort and k is the difference between the maximum and the minimum key values, basically the number of possible keys. So the conclusion, it is only suitable for direct use in situations where the variation in keys is not significantly greater than the number of items. As you can see, if k is small, we are going to end up with a linear algorithm. But if k is huge, then maybe this running time is going to be slower than bubble sort, for example. So we have to make sure that this k is small enough. So we have a one-dimensional array of integers 1, 4, 1, 7, 1, 7, 10 and 3. Okay, we allocate memory, so it's very important that this counting sort is not an in-place algorithm. We definitely need some additional memory. So we allocate memory for an array size k. We want to track and count that how many occurrences are there in the original array for the given key. So what about the algorithm itself? We iterate through the original array. Okay, it takes linear time complexity, not that painful, not that expensive. Then the value in the array will be the index of the temporary array. We just increment the counter there. Then we traverse the array of counters with array size k and print out the values. It will have an ordo k running time. And it's going to yield a numerical ordering, okay. So we allocate an array with size k for the counters. What is k exactly? We will have 10 in this case because the maximum item is 10, the minimum item is 1 in this one-dimensional array. So the k is equal to max minus min plus 1. 10 minus 1 plus 1 is equal to 10. So we need 10 slots, 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. This is why I said that if k is huge, for example the maximum item is 10,000, it means that we have to allocate a one-dimensional array with 10,000 slots. So 10,000 array buckets, and our algorithm is not going to be that efficient. But in this case, if the number of items, so in this case 1, 2, 3, 4, 5, 6, 7, the number of items is approximately equal to the maximum number or the minimum number, basically it is in the range. So in this case, counting sort is going to work just fine. Okay, so first we initialize this counter array. Of course, by default there's going to be zeros in this array buckets. And we have the indices. Okay, indices starts with 0, but we say that this is the first array slot, this is the second array slot, then the third, fourth, fifth and so on. And then we start iterating through our original array. 1. Okay, it is the number 1, so we increment the value in the bucket associated with number 1. What about the next item? The next item is 4. We increment the value in the bucket by 1, where the array slot index is 4. What about the next one? It's 1, so we increment again, where the bucket ID is equal to 1. Then 7, we increment it by 1. Then 1 again, we increment it by 1. Then the 7. Then we increment the bucket with ID 10. Then we increment the bucket with ID 3. So as you can see, we have to iterate through the original array once. It's going to take ordo n linear time complexity, where n is the number of items in the original array. Then we have to iterate through the counter array, which is going to take ordo k running time, and k is the number of items, so the maximum minus the minimum plus 1. Okay, so we have considered all the items in the array in ordo n time. We consider every item in our counter array. The content of the array determines how many times the given index is present in the original array. So for example, we start at the beginning, the content value is 3 and the index is 1, as you can see. What does it mean? That we have 3 items with key 1 in the original array. Okay. So the numerical ordering will be, we have 3 ones, 1, 1, 1. We have 0 item from integer 2. We have a single integer 3. We have a single integer 4. We don't have any 5s. We don't have any 6. We have 2 7s. We have 0, 8. We have 0, 9. And we have a single 10 at the end. So as you can see, we have managed to get the sorted order with the help of the counting sort 1, 1, 1, 3, 4, 7, 7, and 10. Okay, so the overall running time will be, first we have to iterate through the original array, it is ordo n, plus we have to iterate through the counter array in ordo k time complexity. Ordo k plus ordo n is equal to ordo n plus k. The problem, as we have discussed, that k can be very large and the counting sort algorithm will be very slow. What about the pseudocode? We just have a counting array basically. We have to specify the array, the minimum key and the maximum key. How many slots do we need? The max minus min plus 1. This is what we have been discussing. Okay, so max minus min plus 1. That's why counting sort can get slow if this count array is huge. Then we consider every key in the original array in ordo n and increment the counter array according to the right position. And finally, this operation takes ordo k time complexity. We iterate through the counter array, and while the counter array is not 0 at a given position, we have to consider that index as many times as the value in counter array. Okay, it yields the numerical ordering, of course. So that's all about counting sort. Thanks for watching.